Hi everyone, a warm welcome to one and all present here. Today I am going to teach you about the Aerodynamics 1, Unit 1. Myself R. Saravanan, Assistant Professor, Aeronautical Department, Maths. In this Aerodynamic 1 syllabus, in first unit we are going to cover Introduction to Low Speed. In this subtopic contents are Euler equation, incompressible Bernoulli's equation, circulation and velocity, Green's lemma and Stokes theorem, barotropic flow, Kelvin's theorem, streamline, stream function, air-rotational flow, potential function, equipotential lines, elementary flows, and their combinations. In this subject, we basically we have some aerodynamic tools which are necessary for the better understanding of aerodynamic subject. Those are we need to know about basic flow equations, concepts, and theorems. In the basic flow equations, we need to know continuity equation, momentum equation, and energy equation. Um, for what we are studying the basics of the flow described in these equations. In the concepts, we need to know about substantial derivative, streamline, streak line, path line, vorticity and circulation, stream function, and velocity potential. In the theorem, which is basically on mathematics topic, we need to know about Green's lemma, Stokes theorem, and Kelvin's theorem. In the first topic, we need to know we are going to deal with conservation laws. For any fluid system, we need a fluid must satisfy three basic equations. That is continuity equation, momentum equation, and energy equation. In the continuity equation, uh, it uh, it tells us that mass can neither be created nor be destroyed, but can transfer from one place to another. Here, looking at the image below, if consider some 5 kilogram of mass per second of air is flowing at the entry, and it is coming at the outlet, which means how much amount of air at the inlet is flowing, it must be coming out of the uh, object at the outlet. If suppose a 5 kilogram of air per second is entering the nozzle given below, and only 3 kilogram of air per second is leaving out of the nozzle, it tells us some amount of air is accumulating inside the control volume. Here, the control volume is the nozzle. So, if 5 kilogram per second of air is entering and 3 kilogram per second of air is leaving, then 2 kilogram per second of air is accumulating inside the control volume. This is given by the continuity equation. And second one is momentum equation. What momentum equation is telling is momentum is neither be created nor be destroyed. So, conservation of momentum can be proved by proved in three different directions, because if we calculate for all direction, it will be more complicated. So, to avoid such complications, we will deal with specified directions such as momentum equation for x direction, momentum equation for y direction, and momentum equation for z direction. Momentum. What is momentum? The mass into velocity. It gives the moment for an object to flow. It is described as a momentum, mass into velocity. Then third one is conservation of energy. Here we are saying that energy can neither be created nor be destroyed, but energy can be transferred from one form to another. For example, flowing mass of air flowing has a kinetic energy or potential energy, or some form of pressure energy. Similar ways. If initially it is having a kinetic energy, mass into velocity square, finally it is going at some other mass into velocity square, which means initially there is some kinetic energy, and at the outlet it may have a higher, or it may have a lower kinetic energy, which means kinetic energy can be transferred to another form such as potential energy or pressure energy. But remember one thing: energy can neither be created nor be destroyed. It can it can just transformed from one form to another form. So this is just to explain ourselves with the mass flow rate. Mass flow rate is mass of fluid flowing per unit time taken. Generally, we refer density with rho. Here it is given as velocity as v and area as e. So, mass flow rate can be defined as a product of density, velocity, and area. From this, continuity equation also takes place. The product of density, area, and velocity will always remains constant. Uh, Consider if in this nozzle at the throat area, the area will be area of the cross section is very low. At that cross sectional area, very small cross sectional area, velocity will be high. Uh, but at the outlet section, the area of cross section will be high, and which implies that then velocity will be low. So the product of density, area, and velocity always remains constant. Now, coming to the momentum equation, this is based on the Newton's second law: force equals to mass into acceleration, which can also be defined by d by dt of m into v, which is mass into velocity. Physical principal force equals to time rate of change of momentum. There are different types of forces that can act on a body or a flowing fluid. One is body force. This body force doesn't have an control or contact, physical contact over the control surface. It always acts at a distance on the fluid. For example, gravitational forces or electromagnetic force or any other force. Because gravitational force we can experience, but it doesn't have any physical contact. Similarly, second force is surface force. Example for surface force is pressure and shear stresses acting on the control surface. Yes, pressure if some amount of air is present on the surface above or below some control volume surface, it exerts some pressure on the surface, on the control surface. Due to that uh, pressure acting on the surface of the, for example, if you are taking an aerofoil on the surface above and below the contact surface, the pressure surface pressure will be high and low. For example, on that aerofoil, the pressure will on the top surface will be very low. That is high in terms of suction pressure. In the lower part of the surface, the pressure will be high. The pressure always moves from higher pressure to fluid always flows from higher pressure to lower pressure. Since at the bottom surface the pressure is high, and it tends to move from lower part of the aerofoil to the higher surface of the aerofoil, which makes the aerofoil to move in upward direction. Another type of surface force is shear stress. Shear stress it is caused due to the rubbing action, we can say. Uh, when air flows tangentially across the surface of an object, it will cause a shear stress, which is also known as a surface force. Generally, from momentum equation, what we are trying to say is net flow of momentum out of control volume across the surface equals time rate of change of momentum due to unsteady fluctuations of flow properties inside V. Uh, what is the net flow of momentum out of control volumes across surfaces? Considering if we consider a surface, it has different types of forces. As we have already told, what are the different forces means body force, pressure force, viscous force. As the pressure force keeps on increasing, that net force will keep on decreasing. So, as a result, we have arrived at the negative symbol because as long as the pressure is reduced, then velocity kinetic energy will be high, and which will lead to the effective flow of the fluid. There will be some body forces which is represented as a triple integral close to integral over rho f dv, and pressure force which is integrated by minus double integral over the closed surface of pds, and viscous force. So the second one is time rate of change of momentum due to unsteady fluctuations of flow properties inside, which can be represented as two components. First one is a local component, and the second one is a convective component. First one is change in mass with respect to time taken, mass flow rate with respect to time taken. So second one is convective component, which can be represented as rho v dot ds into v. So what we can say from both equations, we can simplify those equations, and we will obtain the equation um, obtained here in the first equation. Simplifying those equation in terms of directions, we can obtain x momentum equation as dou by dou t of rho u plus del dot rho u v equals to minus dou p by dou x plus rho fx plus fx of viscous. Fx of viscous means viscous force in the direction of x. The rho fx is body force minus dou p by dou x is pressure gradient, which causes the motion of the flow. Dou rho u by dou t, which is the local component of momentum, and the delta rho u v is a convective component. Similarly, we can write for the y momentum for in the y direction and z direction, as shown here. These three equations represent the Navier-Stokes equations for a viscous. Generally, when we are providing the momentum equation, which uh, uh, which contains viscous component, it is known as that momentum equations are known as Navier-Stokes equation. If we taken out the body force and viscous component of force in this equation, if we taking them out, then we will obtain the Euler equations, which can be provided as shown in this slide. Next, we are going to arrive at the Bernoulli equation. For the flow is steady, then a local component will vanishes out. Then in the momentum equation, we can simplify it. There we have represented as del dot rho u. We can elaborate them as u dou u by dou x plus v dou u by dou y plus w dou u by dou z equals to minus 1 by rho dou p by dou x. Multiplying the equation by dx, we can obtain the equation which is shown here. Then substituting the equations of streamlines, u into dou u by dou x into dx plus dou u by dou y into dy plus dou u by dou z into dz equals to minus 1 by rho dou p by dou x into dx. Then we can obtain the equation as u du equals to minus 1 by rho dou p by dou x into dx. We can write as a integration form of half du square equals to minus 1 by p 1 by rho dou p by dou x into dx. Similarly, we can write for different directions such as y and z directions, and combining all those equations, we can obtain dp is equal to minus rho v dv. From this equation, integrating this equation, we can obtain p plus half rho v square equals to constant. This is known as Bernoulli's equation.